Yeah, thank you very much, dear Thorsten. It's a great honor and pleasure that you introduced me here at the plenary of ICRA here in Yokohama. It's a fantastic honor, and I'm really looking forward to this. And yeah, I'm also a bit speechless to stand here in front of you, and I try to give you kind of the best I can give you today. So I was thinking when being invited to the plenary, I need to give it a very big title so that anyone, people will come. I was hoping for a few people to come, and then I was kind of making up this title and thought, okay, maybe I will see a few of my friends, but now it's getting full, and now I feel a bit guilty having dragged you here, and I hope that this about hour is worth to stay with me. So talking about the great Robot Accelerator, collective learning of optimal embodied AI. So first of all, before I will go into details, I would actually like to thank the accelerator of my lab, the institute. I have a great pleasure to work with fantastic young researchers, amazing people staying with me also tonight to prepare and not only helping but really being an inspiration, source of inspiration. And it's a great honor and pleasure to work with these fantastic talents and more and more also friends the more they mature and become successful in the world. So I think one of the obvious things that is happening at the moment is that we see more and more robots coming, iterations over iterations over iterations, and now we actually live in a time where humanoids become reality, at least according to media and according to many of the videos. We see more and more videos, which is really amazing to see, and I think it's fantastic that we, compared to the time when I was a student and compared to the times before, my teachers when they were students, it seems that robotics is taking exponential leaps. From the embodiment, it feels it's a decadal problem, so it typically takes 10 to 20 years to actually have a new generation of robots. I was myself involved in one of them, and Thorsten gave some insight on that. I think at the same time, this is kind of the limitation also that we see dramatically having. So my talk today is really about how can we accelerate that? So how can we not only look at robotics as being the embodiment, but also the intelligence, and how can we accelerate both? I think we all agree that on the intelligence level, algorithms, AI has kind of did a great deal in accelerating over the last years. But the same question, obviously, we have in embodiment. So how can we kind of increase the speed? How can we increase the capabilities of robots beyond what we see today? So when I was a student compared to today, when I'm a professor and doing my research, I feel that there is something missing. We need to really speed up in order to keep up with the amazing speed that on the intelligence level is happening. And I have the feeling that with the dawn of AI we have seen the last 10 years, there is so much potential. So how can we really use this human AI cooperation to accelerate that? And this is going to be my talk today. I'll try to give you some insights on my thoughts, but also on some recent results, many unpublished results still, but I wanted to share them at this amazing opportunity. So, and I will discuss today my results along three major hypotheses. The first hypothesis being that zero-shot learning is possible and models are critical to achieve it. The second hypothesis is that autonomous robot design requires cooperative AI grounded in the feedback of physical synthesis. And the third hypothesis, exploiting embodied intelligence requires real-time optimal control. Real-time optimal control. Coming back to many years ago, in the late 70s, early 80s, we have seen many of the pioneers of our field, and these are just a few ones that I have close relationships with, but there's many more, of course, but I think it's clear that Osama, Gerd, and Bruno have been doing tremendous progress in force torque-based interaction, operational space control, collision avoidance, and so on. So they have been really laying the foundation for robots that we nowadays, we heard about the Franca robot, laid the inspiration and the fundamental basis that I could draw from, and many of my colleagues, my students, and so on could draw from. We have obviously all kinds of research, so this is something that we needed to do when I was a student. Robot safety was a big thing back then, because there were kind of the ideas that humans and robots cannot collaborate. Around the mid-2000s, it was kind of common knowledge that according to standards, according to current knowledge, we shouldn't share workspaces, humans and robots. So lots of my work was about that. And back then, at my time at DLR, which was really a great time back then, I was kind of tasked with the idea of, okay, can we actually make robots safe, and how can we quantify the safety levels there? And obviously, I found some interesting results. They were kind of contradicting the previous state of the art, in the sense that, well, maybe we actually have a chance to collaborate, and there's this evidence based on crash testing, but there was kind of hard belief in that. And back then, I kind of, for the first time, thought, okay, there is a, I'm half Finnish, my mother is Finnish, so I thought of the Helsinki Convention, and I kind of did these experiments back then to show that these robots are safe. So this was at night, kind of 6 hours of crash testing with my own body. But I think it led to this kind of understanding that humans and robots can interact with each other in a way safely, and the human kind of is victorious over the machine. As long as the machine is lightweight, safe, and kind of equipped with certain sensors and collision detection algorithms, we kind of have a good time there. At the same time, we kind of was working with KUKA back then, one of the biggest European robot manufacturers, in developing all these collision handling algorithms that many of you probably know. And the idea was really to make these robots safe for interaction, but also to break ground in terms of what I think became this collaborative robotics, soft robots and tactile robots that we see today. So really the kind of the early days of bringing this technology to reality. And this has been a tremendous effort together with Alina Busheffer and Alessandro De Luca back then in developing these systems and really commercializing them, bring them to reality, and I think really being one of the key elements in human-robot collaboration and interaction in the real world. So I think with this kind of basic results, we could really draw after my time at DLR, when we were kind of founding Franca Emica and really building everything from scratch again. Right? So we were actually kind of tasked to build this from scratch. We couldn't kind of draw really from the previous technology because there were some licensing agreements between DLR and KUKA, so we actually had to reinvent everything. And this was kind of a very interesting task, to really think from scratch how to build a robot. This has been more than 10 years ago. Actually, I feel that the Franca system is obviously kind of already a matured kit, and kind of maybe 11 years old nowadays. Back then, the fundamental idea was obviously drawing from this inspiration from the late 70s, early 80s and 90s about torque control, lightweight robots, and so on and so forth, but really bring this to the next level and trying to build a technology that I think nowadays has also been kind of instrumental for the big dawn of humanoids we see nowadays. So obviously, algorithms were always very, very important. So from dynamics models to reflex algorithms, machine learning on the low level, really to handle all the inaccuracies at very high speeds. So there were very, very strong requirements on safety, on accuracy, and so on and so forth, but also on what we call tactile programming languages. So programming languages that actually speak more than just motion, but actually interaction. So forces and velocity at the same time. So very much aligned with the thinking of Stefano Stramigiuli, who is also with us today, and who has been also a great source of inspiration of many things I've been conceptualizing back then together with my teams. So the idea was really to bring robots to life that obviously have all these basic capabilities of torque control, gravity compensation. That was not new back then, but really on the next level, new algorithms that really outperform what has been there before, and is kind of state of the art today, and everybody has access to that, which I think is really, really amazing for me as a researcher. So I'm very glad that we could kind of help the community to have access to torque control, as Osama always says, the only interface that we all need. So I think it's really important that this kind of torque control, compliance, impedance control really became reality, became a widespread technology, and I think nowadays it's not anymore possible to think that robots need to be rigid. They have to be soft, they have to be tactile, they have to be reflexive. All these things have become a reality, but in particular they have to be safe and reflexive also for interaction with the environment. So this has been proprioceptive collision handling, kind of the next generation of what we have been developing together with Alessandro back then, but really kind of to the next level so that we could actually go through certification and safety at some point with these technologies. The main point behind that was really to show not only to have collision detection and reaction, but actually to also be able to control interaction forces and be compliant at the same time without needing to know the environment. So I think soon there's going to be a new IJR paper about unified force impedance control, which is the fundamental control technique behind the Franca system to be able to do all the things that you see nowadays. So this idea behind unified force impedance control was to bring all that together under the energy-aware control framework, something that I've been also working a lot with my student Erfan Shahriari over the last year, who has been really, really important in bringing this together with me to some maturity level. We kind of could solve that from a theoretical level quite fundamentally. The idea being to unify unify impedance control, so being compliant, but also being able to accurately regulate forces and track forces under the stability guarantees of the energy-based frameworks. So all these bases were kind of laying the foundations, and now many of you have access to that, and I'm very proud to have done that. So it's really something that I was not really thinking as an entrepreneur. I was really kind of, actually I founded Franca because I didn't get money from the German government, to be honest. I still have a letter that actually says your ideas are not worth to be followed, signed by Fraunhofer. So for the guys from Fraunhofer, that's something that has always stayed with me, that it's really important to kind of think that these, hopes and dreams in your science, to accelerate your own science, are really the best things to follow. And if you think it's worth it, then I think many other researchers are also thinking it's worth it. And that's kind of what I feel is a very big gift to me. And I'm very thankful for all of you to have made that such a big success. Apart from that, I think just the statistics that I thought was kind of amazing, because I really loved that many people are publishing with the Franca system. And this is kind of last year's publications at the bigger conferences at ICRA, and I think it's quite amazing how many people are working with that system. And yeah, thank you for that. And so it's worth that I spent almost a decade of my life in developing and together with a great team, which now is taking things further for the years ahead. So, but I think what is important at that point, sorry for that, is really that I also want to say that before we go into the part of accelerating on the embodiment, so I think this is kind of the state of the art today, but I just kind of argue that this is something that took quite some time. I want to first talk about the intelligence accelerator. So let's bear with me for a second that we keep the embodiment to be constant, and we try to kind of look at the intelligence and how can we accelerate intelligence in kind of manipulation. So obviously focusing on the interaction with the world. And with this basis of control, I think it's really important to see that many of the things we have been doing and were successful and became commercial also on the industrial sector, more and more were kind of based on this idea of models meets data, you could say. So the first chapter is about the intelligence accelerator. And I think we've all been inspired by lots of the work that went more than a decade ago between Google, OpenAI, who originally started in robotics. And I think it was amazing to see that data is not inherently solving the robotics problem, but also that you can in fact do something with it. So I think it was a great experiment back then, not as successful as the colleagues thought back then, but I think it was a kind of a push towards using more data-intensive algorithms in robotics, which kind of has really drawn a lot of my attention as well. And I always try to bridge the gap between control and machine learning in a way that, using the models that make sense, and then at the point where it really kind of, leverages putting machine learning in place, which I think kind of was an interesting experience to see how far we can take the things then. So in order to really kind of also say something that it's now a bit of a complex graph, but what I wanted to highlight here is the things we have been always trying to do were very ambitious in the sense of manipulation. So meaning micrometer level insertion tolerances, smaller cycle times than 2 seconds as a target. So we always wanted to, keep the X factor at 1, as Tamim Asfour always says, right? So our goal was always to do manipulation in insertion, whether it's at high friction, low friction, at simple primitives or complex primitives. It was not so much about the motion, widespread motion and learning how to move around in the world. It is more about the delicate interaction and really being able to kind of deal with the clearances and tolerances we are all facing in robotics. And this has been our ambition, and I think we try to really solve that problem to some extent. And here you can see some work of Lars and Flo. Lars recently graduated and is, I think, now has recently been commercializing this technology with Franca, is really about the idea of using kind of structured learning approaches which kind of integrate well with the impedance and force impedance control frameworks we have been doing, and lots of nonlinear adaptive control we did with Etienne Baudet from Imperial College to actually really solve very challenging peg and hole problems, such as the key into the hole, in order to then really outperform end-to-end reinforcement learning algorithms and others. So I think what is really important is not so much that you can outperform a reinforcement learner, but it's more that the integration of control and data-driven algorithms really is promising, and you can actually achieve something that becomes reality and that matches both the requirements in terms of insertion tolerances, but also in terms of speed, so cycle time that you want, so performance in the end. And this is something that I believe is extremely important also for us as a community to move forward, not at these two ends of the spectrum, but really try to leverage that much more. And this is a plot that Flo was putting together, which kind of shows why models matter, or from a data-driven perspective. So what you see here is really kind of the idea to increase the model along the x-axis into in this case, it's a DDPG system, and then compare it with our algorithm, which we call PSP. So PSP is kind of this fundamental idea of what we call tactile skills, which is the generalization of, let's say, dynamic movement primitives or dynamical systems to energy-based systems that both create wrenches and twists in the end effector spaces, and then interact with a unified force impedance controller or similar-like architectures, and learn kind of these meta parameters that are in place then. So what you see here now is basically this uninformed architecture that tries to solve the problems we are dealing with here, so micrometer level tolerance insertion tasks. And if you do a naive kind of approach, then obviously with an end-to-end approach, you're simply not able to solve the task. But interestingly, a change in coordinates to operational space level doesn't change anything. But the moment you inform the process in terms of the variances of the forces that are in place, the amplitudes that are in place, it starts to change. The picture starts to change, meaning the time it takes to have some success is obviously still very high, but you have the first successes. And the moment that you actually give the right variances of the contact forces you want or you need to apply for the given task, it starts to shift entirely. So this information of the process, you could call a model, right, kind of changes everything in terms of making also end-to-end algorithms more and more suitable for these tasks. Obviously not yet as high performant as the PSP, but I think there is a road ahead that really kind of converges, I think, in the next years to come, which I thought was kind of interesting to see. So, and then obviously we were kind of interested in, can we not only learn tasks and can we achieve them at industrial grades, so really at tasks that were superhuman, so we were actually faster than all the students in the lab back then. But the fundamental question was also, can we transfer that knowledge, so from one task, being the peg into the hole, to another task, which is the key into the hole. So can we basically warm start and use that kind of skill knowledge to then transfer it to another example. So what we see here is kind of a skill learning algorithm that tries to learn the peg into the hole purely blindly. It just roughly knows where the goal is able to learn it, which is, by the way, really, really tough to insert. But then kind of the system is able to transfer that after it's successful to another example, which we see here. So this is kind of now directly copy-pasting the learn skill to a key into the whole problem, just geometrically scaling the task frame. And then in the end, what is kind of interesting is that you can directly insert. Obviously, it's not optimal yet, but there seems to have happened some transfer. And the next question that we asked ourselves back then is, okay, if we can actually now, solve this machine learning problem or let's say skill learning problem, even just without any big compute powers, this actually runs on standard PCs, and we can now transfer knowledge back and forth, then the question could arise, because we're working with communication people, so what happens if you have a very large network, so inspired by the works we saw before from Google and OpenAI, what happens if we now send around data across the network, and can we kind of create something that could become an evolution, kind of an avalanche effect of exponential nature through the learning network? Obviously, this is highly connected and related to many of the works in collective intelligence, swarm intelligence, network robotics, collaborative learning, and federated learning, but in particular also to the fleet learning systems that Dieter, Sergey, and Peter have been working on over the last more than a decade. Obviously, kind of focusing on this idea of parallelization of learning. So our question was more, can we actually leverage knowledge, translate it to another task, and distribute it back to the network? And what kind of effect can we see if that happens? That's something we called collective learning. So the idea really of basically creating a collective mind that, in a way, every robot becomes as smart as the sum of robots or the collective of the robotic systems. So in a way, what we were kind of working on in the early 2014s, I actually filed a patent on that, which became granted. We did a patent on collective learning, on skill learning. We did lots and lots of kind of theoretical and practical experiments validating that actually this transfer can be used to have more and more kind of transfer among different tasks, among different locations and so on. And we try to bring that forward to the extent that we really build something which we call then collective learning. What we see here now is the difference between isolated learning on a parallel level and the distribution of the knowledge through the network. And we can see kind of an avalanche effect running through the network. This is very new results, just a few weeks old. And what we see here is just a small group of 5 agents that learn 25 collectives. We can see already here kind of this very fast effect that runs through the network to basically acquire skills very quickly. The tail of the system is kind of coming from the distribution distribution. That's at least our explanation from that. But what is kind of interesting is really that you see a dramatic increase, which goes beyond the parallelization of the systems, and really seems to be kind of this incremental learning plus transfer plus connectivity gives you this kind of network effect that obviously has not been there in robot learning so far. So, and I think what is kind of now a very recent result, and this is actually something that just went through tonight, so I wanted to share with you. This is a recent experiment we've been running with lots of industrial tasks, lots of very tight principal things, but also with tools from everyday usage. So really the idea of making the robot a toolbox. And what we see here now is a video in the Deutsche Museum, that's kind of the Smithsonian of Germany, where we run this kind of experiment. And what you see here now is basically the AI factory. So that's a system we have been developing together with my colleagues at TUM, where the collective learning system is running. So this is now 25 dual-arm robots, 50 manipulators in total, and each one is controlled just by a single CPU. The AI runs on that. So pure tactile kind of learning, and these are all the mentioned micrometer tolerances in the insertion. So it's over 100 industrial-grade components, different shapes and sizes, and the idea is how fast can these robots learn if they basically just, push around the knowledge of the skill around the network, and can they learn these kind of skills equally fast as the ones you saw before, the 25 now to the 100. And this is obviously a huge logistic thing for a non-commercial entity, so we're obviously universities, so we really try to kind of be as effective and efficient as possible. And the idea is that all the robots learn autonomously, they continuously share the knowledge, and they draw it from the collective. And this collective learning system is basically, it's in the basement of the Smithsonian, I call it Smithsonian German Museum, Deutsches Museum. And the idea is basically that over the course of action, we want to learn 1 million skills over a month. That's kind of the target we set for the next years to come. And what you see there is Samuel Schneider, who is really running the whole experiment basically alone. So he's just changing the system. And you see how the robots, raise their hand, they are done with it. If you just learn it with one, if you run it with a deep learner, then typically you have sometimes some, let's say, successes. Here, the robots are running just over a course of a few hours, and they now totally learned the entire task. So this is what you see here, has been kind of the accelerator 70 times, and this is the last one that was learned. So in total, 100 skills in, I think it was now 2 or 3 hours. And that's kind of on industrial grade. So all of them could now, in principle, be deployed, at least from the performance level. Obviously not from the implementation, but from the performance level. And what you see is something that we have been building in Bavaria, in Munich, together with my colleagues from Alois, Eckhard, Achim, Klaus, and others. Darius also very strongly involved. It's the Bavarian AI factory, and the idea of this is basically to build a reconfigurable factory that can basically take a desired building plan and then build kind of a manufacturing system on as a service, basically, that is able to use previous skills to apply them to new problems, but in particular learn them on site and really be scalable in a way. So this is something we've been building over the last years. And I think this year we're going to have Coral in Munich, so in case you're around, we're going to have a visit also there. So hope that many of you will join us at Coral in Munich this year. So the result of what we saw there was actually that in this pit stop Charlie, this is the results from tonight. We actually could see this collective effect here. So this is the kind of isolated learning, parallel learning, and then going to the collective learning effect. The idea was to learn the 100 tasks with 10 agents, and as I said, this kind of effect could be validated. However, there are certain limitations still. In particular, obviously, the order is important. So the schedule dramatically changes what can happen there. So we're very happy that we could do that, but one thing that we recently saw is really that this kind of algorithms are actually able to create single-shot learning incidents. So what we see here is an early experiment, and what you see here is the Xi equals 1. This is always when single-shot learning happens, and you can see here different schedules for the same sets of tasks, and you can see how the schedule really matters. So coming from 5 to 2 to 13, then to 1. So depending on how you schedule the tasks, then obviously the robots are able to learn better, or faster, or even worse. It can also be detrimental. So it's very important to understand that zero-shot learning can be observed for the right schedules. So that's something that is really important. I think that this kind of big-scale experiments now becomes evident, and that's something we want to work on in the future much, much more intensively. Another question we're asking is, can we actually use kind of a cardinal skill system? So we call this the busy box, from Peter So, who's also a student in my lab. He has been building this box to basically learn kind of principal skills, and the question we asked, can we actually kind of scale up the speed of all the skills you saw before? I think these were 25 in this example. If you have learned kind of different skills from a different environment and then warm start basically this collective learning system, and the answer is yes. But at the moment we always see this tail from the distribution, which we still try to explain well, but it's very clear that here is a very huge learning effect. The closer you come to the end, it seems that the harder the skills get, the harder it is actually to kind of resonate with this effect. Okay, so I think the key insight I wanted to share with you from the collective learning is that this, I think, seems to be the foundation of a democratized kind of a superintelligence, meaning that all the robots can share that knowledge and they can basically create as one collective to really, I think now, can be set up to learn thousands of tasks if you have such a system in place, and really kind of do incremental and transfer learning and really leverage that in a constructive way, which I think was largely missing so far in the way that we have been doing machine learning, especially also in control. So I obviously think this is the case also in control. So let's come to the second chapter. Now that I talked about kind of recent results and the intelligence level, I think what is at least equally important is how can we scale up the embodiment development. So if we think about not anymore keeping the embodiment constant, but really trying to get to the embodiment accelerator, then I think it's really important that we first need to start with the human. So the human designer needs to be accelerated. The what, the knowledge, and the creativity of the human is unmatched. And we need to basically circumvent that and get a rapid design of optimal robot morphologies tailored to the intended tasks, however, wrapped around the human. So we need to basically work on the morphology and innate dynamics to be kind of assisted by AI. We need to be able to assist the design and implementation. We need to be able to build a policy generator that is assistive, and we need to be able to do the performance evaluation autonomously. I will today not talk about the performance evaluation because I think this is something that comes without saying. So in a way, we're looking for a Jarvis, right? So if you think about Iron Man, so I'm dreaming of a Jarvis that helps me to basically create my own robots. Or maybe this is a student who is able to, instead of spending as I did a decade or more to develop a robot, bring it to life, and then make it part of our community, maybe we can do this at orders of magnitude faster. That would be my dream. So, and I think this is a very important dream for robotics because this is kind of the major hurdle that we see. We did not yet have our GPU day, and I think we as a robotics community really urgently need that. So let's start with morphology and innate dynamics. What do I mean by that? So morphology and innate dynamics kind of is the idea of looking at a phenomenon, building template dynamics that kind of roughly explain on the simplest mathematical description what I'm looking at, and then build anchor dynamics, so essentially systemic interpretations of morphology and innate dynamics that are able to render the right behavior in a physically interpretable and morphologically meaningful level. So I think we can cluster this into the what do we want to do? That's typically the human who says what the robot is supposed to do. And then the idea would be, can we automatically create the how? That would be a fantastic thing to be able to do. So we basically need to take the inspiration from a performance evaluation, so kind of telling you could say the specification, if you think of it that way. And then can we actually automatically build such a, from a phenomenological what, can we create the template dynamics, the anchor dynamics automatically? All right, so this is not a new thing. Obviously, we have seen template dynamics, especially in locomotion, everywhere. So there's all these kind of fantastic models that have explained locomotion and I think have always driven the amazing humanoid developments we have seen over the last years. Starting from the classical slip model, then going to more complex things like the VPP system, also interacting with the slip model that we've been working on, but then also coming to the ULT model that tries to explain more complex behaviors. However, if we go for manipulation, is that largely missing? So we are typically thinking in motion plans and configuration spaces and things like that. Operational spaces, I think, of the most important representation that has been developed by Osama and really kind of also formed my thinking of robotics. And I really think that this is something we need to more formalize to also think in these template models. So if you think about templates, we could obviously have rigid systems that basically do motion plans. Then we could have series elastic systems that are basically doing resonance systems and so on and so forth. So this is a work we've been doing back then at DLR, blind dribbling, which I think was a pretty cool thing. and kind of showing how much you can redo with a template model, then it's being driven by much more complex kind of control architecture. Okay, so if this is kind of the idea, then obviously SEA, as one example, could be thought as a great idea to run. However, it kind of turns out that SEA is not the best idea to actually do timed resonance templates. So we actually need to really work on more complex patterns to kind of, not only think that coordinated oscillations, which is for throwing and running and so on and so forth, a great idea. But I myself, as many of you, have been fighting with the idea of putting springs in the joint space and then dealing with this idea of almost chaotic nonlinear oscillations and trying to control them, which is ultimately, retrospectively, was a very bad idea, I think. So we actually need to think about very different ideas, and cross-coupling came into mind, which in locomotion, I think they are very much ahead of us in manipulation in these terms, in coordination questions, is obviously something that works much better, as we saw here. So SEA is kind of a bad template for one DOF, but also for multiple DOFs. So if we now go further, and try to think on the anchor dynamics, so not on the template dynamics, but actually now come more closer to the actual, system that is closer to the robot. Then obviously this template dynamics gets input, and now the question is how does the morphology and inner dynamics look like that we want to realize that later on guide the development and synthesis of the robot. And what we see here now is basically kind of again a template model that is not that well chosen. This is a series elastic system, so with intrinsic compliance, we can validate the same thing with the Franca that is actively compliant. So it's very bad in coordinating motions. Obviously, this is multiple oscillations going on. So and if we look at cross-coupling, then we can start to actually generate via, for example, antagonistic actuation as a physical embodiment. You could say this kind of very coordinated motion that goes over the entire kinematic chain. So that's also an interpretation of the cross-coupling problem. Actually, antagonistic systems can be interpreted as cross-coupling implementation in order to do this coordination. So which I think is really important because it makes planning, control, and everything much easier the moment you think about that, and you don't try to really rectify a kind of a diagonal stiffness matrix that has inherent limitations by design. Okay, so if we kind of now go further and think about the anchor dynamics, the next thing is obviously to build the morphology. So some work from a really gifted student of mine, Fernando, who has been working on kind of creating the self of a robot. So he was recently in this Science Robotics paper kind of proposing how to create only from proprioception autonomously the entire body schema of a robot, so the entire kinematics from pure sensory measurements. And then also creating the dynamics of the robot also from scratch, you could say. And I think it's really interesting if you see how this morphology of the system basically being defined as the self, meaning the numbers of degrees of freedom, the connectivity, the adjacency matrices, the kinematics, dynamics, and so on, can in fact be fully automated or automatically generated the moment you understand the pipeline of algorithms that have to be concatenated with each other. Next question is obviously can we solve that problem on the next anchor system? And we have been proposing recently a system we call bi-stiffness actuation. So the idea of instantaneous binary stiffness adaptation, so kind of this ideal implementation, you could say, of the variable stiffness system where you kind of can jump in stiffnesses. So between full stiffness and zero stiffness. And this is a system that is also being, I think, presented here at several papers at this conference by Mehmet and Dennis. And I think also Edmundo is here, who has been these three were the main developers of that paradigm, and I'm going to show you a little bit about that in a second. And this kind of idea was basically that the embodiment has to render the desired dynamics, or at least come close to it. And this fundamental idea, I think in locomotion, is much more established than in manipulation. And I think we actually have a big chance of creating novel robotic systems that can really render the things we want them to do. But we first need to explain, similar to the locomotion idea of template dynamics and anchor dynamics, how to constructively go that path. So now let's come to the design and implementation. That's something that was also just realized tonight. So I really hope that you find that interesting. I was kind of fascinated by this idea. So the idea of autonomous robot evolution, you could say. So the idea of having a design co-pilot, right? So really this kind of Jarvis of Iron Man. So can we essentially design in a collaborative process, do the robot synthesis automatically, and then actually have the physical embodiment? I know many people are working on that, but I think it's interesting to think of this not only being a purely design question, but really physically manifested in the physical world and trying to get the feedback in the process itself. So kind of a cyber-physical evolution, one could say. And what I mean by that is also on the collaborative discovery process, I think it's really important that we think of the human being the center of that design process. So if we want to have a knowledge discovery model trying to kind of discover the space of designs, kind of trying to get to the optimal design given my requirements and specifications, then I think the question is how can we actually combine the human and the AI intellect in a way that we maximally kind of create progress in this kind of design space. So the big question is fundamentally that we kind of want to also generate, I call this the orbit cascades of evolution, where we kind of try to understand the structure and the architecture of the system we want to build, and then build all these subloops that try to optimize basically what's going on there. So Johannes Ringwald is doing his thesis on this topic, and he's doing a great deal of work and really trying to get a kind of a little evolution running that actually is physically manifested. He had some papers recently on that, on automatically printing robots based on their feedback in the real world. So basically the real world feeds back into creating new robot designs, robot in basically still on the mechanism level mainly, but really interesting how much you can accelerate the optimization in the AI or digital world by basically grounding through a real-world robot synthesis. So one thing that we have been working on with Diego for several years has been also trying to automatically design drive trains. So for example, trying to combine engineering knowledge with data-driven ideas. So can we actually approximate the motion and synergy spaces of the human by basically integrating the drivetrain in the hand, such that we can do delicate manipulation tasks. So we're trying to come from different angles. This is more on the computational level, so coming from human information and kind of design paradigms that come from engineering knowledge. But I think what is maybe even more interesting is, can we actually try to physically embed this kind of optimization? So not only train, build and optimize, but I've been building robots. I want to feel them. I want to see what they do, and it's really hard to do this in an automatic fashion, right? We call them prototypes. We try to kind of understand how can we accelerate, but it's really hard to understand it if you don't think about the structure of the machinery that actually has to drive that design and synthesis process. So let's take hands for an example. I mean, hands is kind of the most complex thing we can think of. Still today, there is no hand that even comes close to our hands. I mean, I think we're light years away from that, to be honest. If it's not, I'm not sure what is more than light years in this analogy, but it's really ridiculous how far we are away from the human hand, especially in terms of capability, right? So, I think in terms of tactility, sensor feedback, dexterity, learning ability, this is far beyond. But I think what is clear is, we need fingertips, right? So let's think about the idea of, can we automatically generate fingertips at least? Because these are the mechanical interfaces to the object or to the world that we actually interact with. So there's countless hand morphologies, but in the end we want to have the best fingertips, regardless of the morphology of the hand, because these are the fundamental interacting kind of elements with the object. So can we actually, find a universal fingertip kind of idea? Obviously, this is a very bold question, but we try to find some interesting results. It's very tiny, but I think it's worth sharing. And what we have been working on, this is kind of the autonomous evolution machine that Johannes has been building. So obviously, there is a task that you have to do. So let's take, for example, Ethernet cable, want to insert it. If you just look at it from the pure geometric point of view, right, which we mostly do if we kind of try to do grasp planning and so on, then the idea of pushing a button has to be implemented actively. So there is no way of the functionality is not built in the geometric plan. So the question we asked was, as a one use case, can this machine actually build kind of a fingertip that automatically tries to push things in order to deal with these functional representations on the system that we're grasping. So the idea was here. This is actually just ran tonight. Is that the robot is grasping kind of templates that are being printed. So he's now, we had an evolutionary algorithm trying to guess the best end effector. So you could see that he's trying to push a little knob. So he's building this knob. And now the second robot is grasping the fingers. And as you could see there, sorry, I just need to stop here. So here is this kind of, inlet that you see, and it's actually a button that you have to push. But the robot has no idea that there is a button. And the question is, can we actually design a fingertip that ultimately ends up in pushing this button without knowing that the button is there? And this sounds like a almost too naive statement and too naive question than to be considering. But if you just do that on a computational level, then obviously you will never find that button, right? It's not there. It's not there in grasp planning. So the question is, can this morphology actually automatically generate this kind of push into the system? And this was something that was actually really part of his main achievement in the thesis, that he's building now these automatic fingertip designs that are grounded in reality. He's then optimizing again in an evolutionary sense, kind of informed by the human who's kind of proposing some designs. And this kind of machinery runs and tries to create this tiny nudge that is then in the end able to grasp the button. And just tonight he was actually able to, so this is real data, so you can see here the evolution going on over iterations, and I think above iteration 20 he was really kind of reliably hitting the button. So that's kind of a first step towards automatically, within, I think this took about 1 hour until this was then created, that you can create parts of a robot fully autonomously. And I thought this was really kind of interesting. Here you can see how the finger starts to grow, the little finger, in order to then push the button, and the functionality of the opening the lid is basically being fed back to the evolutionary system. Could obviously be also a reinforcement learner. Okay, so but I think kind of on a long term, I think it's really important that we think of really augmenting the designers. So from unexperienced humans to experienced humans to inform us by AI to really scale us up. So in my wildest dreams, we would have robots that could, or AI design system that could really be used for automatically scaling up our design processes, so that we can have thousands of designs parallelly being hypothesized, synthesized, tested out, and then in the end, in a day or in a week, at least in a month, we might have a robot that actually does what we want it to do. So that's a tiny step in this direction, but I think it's super interesting. And in total, I think it's kind of in the line of thinking of John von Neumann with his self-reproducing automata. It's kind of in alignment with this very nice NASA comic I always like to think of. It was actually published in the year I was born, so I think that's the spirit. And then ultimately also with Konrad Zuse, who's the inventor of the computer, the German actually, and he was also trying to build a self-assembly machine. So this idea of self-assembly, self-reproduction, I think is super interesting. And this also was led in the Franka, development back then. So the main point about the Franka system back then was also to automatically assemble that system and be able to self-reproduce, to be scalable, right? So this was the first robot that was really being assembled by, its brothers and sisters, you could say, and the first automatic robot assembly system that was there. So in this line of thinking, I think this is interesting. Okay, and then because this is, I think, the last Franka system I wanted to show, I also thought that this is a very nice, kind of occasion to give you the back story of Franka Imica and why it was called Franka Imica, because today also my kids are here. And the biggest wonder is obviously why was it called Franka Imica? I was asked many times, and I always said, well, when I write my memoirs, which I will never write, obviously, not famous enough for that, but then I wanted to share that. But I thought a plenary is a very nice occasion to share it, because now you cannot run away, you've got to listen to that. And so Franka is my eldest daughter. She's 11 and she's here. So, and she has been the inspiration of Franka Imica and also of the logo. So if you think about the logo of Franka Imica, that's actually my daughter. Yeah? Franka, who sits with us and who I really love dearly. And Imica is actually the combination of, back then I had only 2 kids, right now I have 3, they're all here. The Imica is my son, Emil, and the second part is Franka, Imica. So that's the 2 sources of inspiration of Franka Imica. And I actually asked them to be here, and maybe you give me help me to give an applause. And where are they? I would like to say thank you so much for being an inspiration. Okay, so let's come to the key insight 2. That is, I'm not sure, I have to stop. I still have 15 minutes. So key insight 2. So the cooperative human AI robot synthesis, and this is very humble, so please don't be too mad at me that I try to say that we think we can help design and build the components of optimal embodiments. I know a mechanical engineer would never say that. I'm a engineer, electric engineer and a computer scientist, I'm allowed to say that. I know that the mechanical engineer would now strongly disagree with me, but I think it is possible, and I really hope that we can actually accelerate the design of robots. Okay, let's come to the policy generator. That's the last part I wanted to say, and I think it is really about the optimal AI. I mean, we have been working on various motion planning, kinodynamic policies, amazing work by Osama, by Lydia, by Steve Laval and Stefan, and many, many others who have been, really transforming our field. In generating motion planning. We have ourselves also been working on kind of real-time motion planning together with Rudiman Laha, who's also here with us, a student of mine who's hopefully soon graduating. So we recently had a TRO paper on kind of, bridging the gap between multi-agent systems and dynamical systems. For many years we've been working on that, so to try to really do real-time motion planning in dynamic environments, which I think is really successful even for constrained systems such as bimanual and so on. But I think what is kind of clear is that these systems are dynamic for the environment, but not dynamic for the robot. So the internal dynamics are basically not respected. So in a way, I think what is really important in order to bridge that gap, this is an experiment that we did back then at DLR. So if you want to do kinodynamic motion planning, you can only work on that level. So you cannot encode the embodied intelligence of the system. So if we actually develop all that systems I was showing you, cirrus elastic, kind of antagonistic systems with elasticities, all the many things we've been seeing, then I think it's pretty clear that we actually cannot leverage that if we just work on kinodynamic level. Whether it's collision avoidance or not, you will never exploit the elasticities in the joint. You will never exploit the inertial dynamics. You will never exploit decoupling that you can do in principle by clutch systems. So I think it's kind of between rigid, and this is an amazing work by Ishikawa many years ago. I still remember when I saw these videos for the first time, I was blown away. I still think that many of these works were underappreciated, and this has been amazing. Especially if you think about the dribbling with the two fingers, I always have to talk about that. But what was really interesting back then, when I was at DLR, was this idea of using dynamics, elasticities to store, release energy, and have graceful motions. However, it was a problem of obviously optimal control. So you need to really work on the optimal control problem. It's a pain. It takes forever. It's really hard to find a solver that actually does it. And we all know that. And this is a very, very hard problem, especially if you don't work on template dynamics, simplified dynamics, which never reach to full optimality. But if you really want to kind of go on that policy level on optimal control, then obviously we want to have closed form solutions, but they don't exist most of the time, especially for nonlinear systems. So there have been many numerical solutions since the 60s. There has been model predictive control since the mid of 80s, at least the first versions. And then also the neurodynamic programming ideas going more and more towards reinforcement learning. And I think it's kind of amazing, how much has been done there, but at the same time, it's also clear that there have been lots of limitations. So all these classifications that you see here, I think are some milestone experiments. The combination of reinforcement learning with optimal control, I think, was really important for our field, but also it has been not serving the purpose till today. Because if you really want to exploit the dynamics, there's still something missing. So I think what is really important is that we kind of remember that if we look at, this idea of exploiting dynamics, then most of the time we try to simplify dynamics. But with this, we automatically already become suboptimal in the way what we do. So, and what we've been working on starting around 2012 for the first time publishing that was what we called an optimal motion framework. And the idea was essentially that we use optimal control. We embrace it. I mean, it takes forever and it's annoying and it takes a lot of time. But why don't we just, solve optimal control offline many, many times? And instead of teaching by demonstration, where it's impossible to kind of, excite the dynamics, can we not learn and optimize that, encode it into, whatever kind of representation? Back then, neural network were not such a big thing yet, and it was hard to encode it in there. But anyhow, and then generalize in real time. And hopefully, with this, if we have the right method, we could actually generate, optimal control in real time. Wouldn't that be amazing? That would be the dream of a control scientist, to solve this grand challenge of optimal control in real time. So, but obviously we need to solve the compute problem. And we have been kind of working back then with many colleagues. Roman Weitschat was there, obviously with Aline, with all the amazing mechanical engineers at DLR, to kind of, work on making the Hazy throw. And then kind of, working on that work for several years. Then I went my own path. We kind of halted this idea a little bit, and now we restarted some years ago. And I think I have some results that I wanted to share with you that I think are very promising and very interesting for us as a field, I hope. So some years later, I think it was Oliver Strass and also Katja Wohnbauer, they were kind of basically following this idea, so encoding optimal control directly based on Gaussian processes. In our work, what we were doing were encoding optimal control solutions in dynamic movement primitives, because I think it's, I like second order equations, obviously, and then execute really near-time optimal motion in real time. So actually the solutions we found were very close to the theoretical optimum in real time, which I think is an important milestone. All right, then more and more work has been happening, and the last years we saw also more and more neural networks being used for these kind of ideas. Obviously, lots of applications. I will not go into details because I think this is now getting out of time. So, but then in the end, I think what we see now is, for example, neural ODEs and others. Also now more and more, we recently had a paper at IFAC that actually could show that with DMPs you can in fact actually really generalize in real time optimality for certain approaches. So coming back to the idea of what we have been doing, so the optimal motion framework, as we call it, is basically getting a task description, so an optimal control problem, then we solve many of these systems, encode them into kind of a system, in our case a DMP, and then try to generalize in real time given a new task. That was the fundamental idea. So as you can see here, an optimization problem, optimal data, encoding it into a large system of ODEs, and then generalizing in real time with a heuristic that turned out to be working well. There's many versions of that, so DMP, LSTMs, foundation models, and so on. So we've been working on many of them at the moment. And we try to show that this idea of really learning can really be done very simply, right? So we actually kind of see that the embodiment plays a major role. So what we see here is the minimum time reaching problem. That's the benchmark I want to discuss quickly with you. This minimum time benchmark, minimum time reaching is showing here that we can essentially leverage the dynamics. So these are the different morphologies. So the optimalities of it depending on the morphology. As I said before, that's what we would call embodied intelligence. And then what you see here now is the trajectories that you would get, for example, for a rigid robot, right? So there's a obviously pretty clear Pontryagin maximum-based motion that you see here. The control is pretty clear. If you now go for the SCA, then you obviously get a wobbly motion, as I said, so the embodiment is not that great for this kind of problem of getting optimally somewhere. It's shaking a lot. If you have a system that is, if you have a system that is now basically being coupling based, then you can really move very gracefully and very nicely, so it's compliant, but it kind of regulates itself to be very nice and smooth if it goes from A to B. So the cross coupling is really important here. The input is also important. The same thing you can do with VSA, so variable stiffness actuation. So if you can control the stiffness, this is also really working well, and so on and so forth. So you can create all these dynamics, and you can see that you can solve the optimal control problem offline and then really encode them. So now the question is, how can we encode them, and how optimal is the encoding if we generalize it? So what we see here now is basically nonlinear MPC as an encoder that does not work so well. The LSTM is also not working so well. So we're actually doing the optimal reaching and try to actually catch the ball with real-time generalization architecture. So this actually runs at a kilohertz. So we encode the optimal control into the different learning and generalization architectures. As I said, an MPC, then the LSTM, then we did some further generalizations on polynomial basis, and in the end with a DMP. It seemed that the DMP, at least as of today, has been the most successful encoding. So the DMP was really able to generate in real time these optimal motion trajectories. The question that we could ask is, how optimal is it? And this is something that we can value. In the end, this is kind of the result we have. So for different tasks, nonlinear MPC was not working so well. Maybe there's an implementation problem still, but still. LSTM kind of performed sometimes. Polynomial, we also had some foundation model that we still couldn't make work. DMP was working quite well, which was kind of, I think, also what we expected, but still we're not married to that. But I think what is more important is that also the data can really be used, that you can really, do very, very tight and interactive. Depending on how much data you use, you can find very tight representations in the cost space. So you can actually represent the entire cost value of the system depending on how much data you have. So it's actually able to bring down the optimality error to almost negligible. So depending on whether you do interpolation or extrapolation, or how much kernels do you use, and here you can see how they basically become essentially in the end a full generalization. All right, so I think in total what I wanted to give as a take-home message here is that on the policy level, I think the more we will go into more interesting dynamics that are not just rigid body dynamics, but really compliant, energy storage, energy generation, and so on and so forth, the more we will need optimal control and its realization in real time. Unfortunately, most of the things cannot be generalized in real time. Obviously, numerical solutions suffer the problem of not being able to encode and generalize. But then in the end, we were able indeed to find a very good encoding that seems to work really well. So it seems like very promising results, and I think this is really a new path that we can go forward in the next time. What you see here now is that it actually works also on the throwing. So this is the newest system we've been developing. It's still on principal stage, but it's actually fully BSA, so you can basically decouple the system. This is a lower hand throw. You can see how really the dynamic decoupling between the different joints can happen. The same thing for an overhead throw. So we really can now use inertial coupling systemically in real time with an optimal control solver that actually gets the job done, which I think is a very promising direction. So it's kind of more and more getting into the idea of, optimal AI can be achieved. I think it's absolutely possible. The results show that. And I think that the holy grail of real-time optimal control might actually be within reach. So it's really worth to think of how to integrate models, optimal control, and machine learning together. I think we in robotics can really leverage from that. It's a very, very promising direction. I can only encourage also the young students to follow that path and don't just give in to Mephisto. You will only make Gretchen suffer. And that's it. Thank you very much. It was a great pleasure.